Hey everybody, it's Eugene Liscio here. Welcome to Click 3D. This is the program where we talk about photogrammetry and how you can use something as simple as a digital camera to create some really beautiful 3D models. Today, what I thought we would do is have a guest. This is our second guest on the little program here. And what we're going to be talking about is the Sift algorithm. Now, for those of you that don't know what the Sift algorithm is, it stands for scale-invariant feature transform. And it was first created by Dr. David Lowe at the University of British Columbia, somewhere around the 2000s or late 90s. And a lot of people don't appreciate what the Sift algorithm actually does. And so that's why my guest today is Dr. Cyrill Stachniss, and he's from the University of Bonn in Germany. And he's going to be talking to us about what this is all about and what it means. Dr. Cyrill Stachniss, how are you, sir?
Hello, I'm fine. Thank you very much.
All right, great.
Thank you.
Thank you for being here. It's great. Before I begin, I want to give people some background about you and your work and that sort of thing, and how you got into your area. So maybe give us just a little bit of background regarding yourself.
Sure. So I started originally out with physics until my bachelor, and then realized that that's not the path that I want to take, and changed to computer science. Did my master's in computer science, started a PhD, and started to be interested in robots. And so I spent most of my career doing robotics, mostly at the University of Freiburg in Germany. But then kind of 7 years from now, changed the field a little bit towards photogrammetry, which is, from the application point of view, a bit different to robotics, but from the algorithms point of view, what lies behind it, very similar to robotics or to robot vision, where you combine robotics with computer vision. And so since around 7 years, I'm working at the intersection of robotics and photogrammetry. So doing a lot of tasks of image interpretation, image analysis, 3D reconstruction, but not only with camera data, also with LiDAR data. And so that's the area where I'm in since approximately 7 years now.
Nice. So actually, I saw you online, and that's where I actually found you. And just for those that are interested, I want to give you a great plug, because I think you have a series. It's called 5 Minutes with Cyrill, and a whole bunch of really, really interesting information in many different areas of sort of computer vision, photogrammetry, all those sort of things. So yeah, they can look you up, I guess, just under your name on YouTube, and it'll definitely pop up. Yeah.
Thank you.
Yeah, good job there. So what I want to talk about today is Sift, and I've seen some different presentations on it. And when I teach my photogrammetry classes, a lot of the students don't appreciate what it does. So it's just like, you click a button and stuff happens. And especially today, it happens so quickly. And I've even spoken to people who do, for example, image fraud and detecting fraud in images and such. And the Sift function is actually quite a robust function. Yeah. So let me ask you, what can you tell us sort of about the implementation of Sift and the impact that it's had? Like sort of what is it? Let's start with maybe what it is or what it does.
Yeah, so basically the Sift algorithm, or the Sift descriptor, is a way for describing local image content. And so the basic idea is that you want to give a signature to a local area in an image. So you may ask yourself first, why should I care about that? Why am I interested in that? So most of the 3D reconstruction algorithms that we are actually developing require us to know distinct points, or to be able to identify distinct points in images. So for example, we have multiple photos of the same scene, and we need to identify which point in the scene is seen in picture 1, picture 2, picture 3. We really need to pinpoint them down very precisely. And that's a task which was traditionally done by humans. So you had human operators, for example, analyzing aerial images in a time far before we had computers, by basically manually selecting distinct points. So the user was interpreting the image and then selecting exactly the same point in multiple images. Yeah. And that's something that the Sift algorithm tries to automate. So first, we have a technique that looks for so-called key points, or for locally distinct points, so points that stand out given the local surrounding. And then the signature or the descriptor that we want to compute around such a key point basically encodes how this point looks like, basically a signature of the local surrounding. You can see it like your signature. So I have a signature, different signature than you have. And by seeing our signature, you can say, okay, this must be Eugene, or this must be Cyrill. And this is very similar for the visual image content. So you have a point and you want to describe the local surrounding. And Sift basically does this based on gradient information. So it checks how do the intensity values differ in those local regions, because it turns out that the absolute color value or the absolute intensity value in terms of how bright it is changing a lot based on your exposure, based on there's sunlight outside, though they change actually quite substantially. It's very hard to do this just based on intensity information.
I see.
But if you look to the changes in intensity, so things like corners or other strong gradients, that's actually pretty robust under illumination changes. And that is a pattern that the Sift descriptor basically looks for.
Yeah, your point about manual. So when I began with photogrammetry way back in 2006, it was manual. So I was clicking this image, clicking points and trying to relate them all. And it was, only a few years before that sort of the Sift started making its way into some of these software programs. Now, one of the things that I had seen is that, or one of the ways that it tries to sort of narrow in on some points is it does something, and maybe you can describe this for me, but it'll take the image and it actually reduces it in scale, and then it looks for these high contrast areas as well. I don't remember the term, if it was Gaussian or something like this, but
yeah.
Exactly.
So two different things come to the game. One thing is that you look into the thing with the Gaussian differently blurred images. So you're basically blurring your image, like in Photoshop, you add a Gaussian blur, and you basically generate differently blurred versions of your image, and then you subtract those images from each other. So this is one way how you actually try to find locally distinct points. So these are basically points which stand out with respect to their local surrounding and also with respect to this blur.
Right.
And the other thing is this image parameter that you were probably referring to, that you basically scale down the image. So let's say you have an image of 1000 by 1000 pixels. You may scale it down to 500 by 500, and then 250 by 250, and so on and so forth. So you make it gradually smaller and perform exactly the same operations on these differently scaled images. So why are we doing this? The main reason for doing this is because you want to be independent of the viewpoint, in the sense, if you take a picture of the scene and you go closer to the scene, the scene will appear larger in your image. And you want to be able to track those distinct points independent of the scale. And this is basically a trick to add a scale invariance to a descriptor, so that the signature that you have is independent from how close you are to the object you're picturing. And therefore, you basically do the same job just multiple times on differently scaled images. So it's more work, so to say, but it allows you to get this independence of the viewpoint, at least to some degree.
So does adding the Gaussian blur, for example, if you have very strong features, when you blur them, they're still quite strong, or they're still apparent, whereas something that's very minute will disappear when you do a blur. So how does that help? How does the blurring help?
Yes, so what you're basically looking into strong gradients or strong changes in this blurring pyramid. So you're starting with extremely blurred images and then reducing the blur. And depending on the level of blur, so you basically start with a Gaussian blur of 1, then 2, 4, 8, 16. So you dramatically increase the blurring effect. And this leads to different things popping out. This can be corners, for example, where you have a strong change in those Gaussians, or this can also be larger blobs, which then also can generate a feature because a point or larger area stands out from its surrounding just at a different scale. And we are basically, it's important to note that we're not looking to the Gaussian itself, we are looking to what's called difference of Gaussian. So we're always subtracting one blur from another, and only basically the difference in the blur stands out. And this basically allows you to generate locally distinct points at different blurring levels, so to say, or at different magnitudes.
Okay. And so the Sift function, like, so for example, with a lot of different software packages that I use, like Agisoft Medshape, 3ds Zephyr, and things like that, this key point extraction and feature matching happens actually really, really quickly. Yep. And has that been sort of optimized over the years, or what helps it go so fast?
Well, the funny thing is that actually in the old days when I started with that, actually extracting the Sift feature was a super expensive operation. So it was also computationally expensive, and there are actually a lot of variants of Sift which try to make Sift faster or have faster to compute features. So one popular one is Surf, which is a speeded up version of the Sift descriptor, which tries to speed up operations. But what you're basically doing in order to compute those key points, you're basically for a key point, selecting the surrounding pixels and basically check for gradients. So you need to compute basically a first derivative of that image function, which you can do quite quickly, and then basically check for those gradients. So where's a strong gradient, in which direction? And you build a distribution or a histogram over those gradients. And then this histogram, so this distribution of gradients, gives you the signature. So you need to do a lot of operations. But of course, it's much, much faster than doing this by hand. But there's actually a large number of other features, so-called binary features. There was one example, which are orders of magnitudes faster than Sift. They may be less expressive or have certainly different properties, but they're also extremely quickly to produce, and therefore a lot of approaches that look for real-time performance. So if you have your mobile phone and you move your mobile phone through the environment and you want to, at whatever 60 frames per second, track distinct points in the scene, then Sift may not be the best choice unless you can use hardware acceleration for doing this. So our GPUs today can do a lot of the operations that we're doing and speed up the computation. So this definitely helps as well. But whatever, if you have mobile devices, especially 15 years ago, when you had no GPU in your mobile systems, actually Sift was a key bottleneck, taking half a second for a regular image just to compute the Sift features in there.
So when comparing a couple of images, so for example, if you have just two images, in some cases, like I like some of these programs will actually show you the feature matches, which is because you can see, okay, I've got weak matches or I've got strong matches. And of course, two images which are, well, the more similar they are, then the more matches there should be. But there's usually a limit, right? A lot of these programs will say, look, once you hit a certain limit of key point, if I've got 10,000 key points, just move on to the next one. So
that's true.
A limiting factor?
I think we have to distinguish two different things here. The first thing is the computation of the key points itself in one image. That's not the limiting factor. The problem is the search for correspondences. So if you have 10,000 images, 10,000 Sift features in image number 1 and 10,000 Sift features in image number 2, you actually have a quadratic number of possible combinations. And this is really what kills you, especially if you have large image collections. So you're absolutely right that finding the correspondences between those Sift features extracted from different images, this is the super computational task. And if you do 3 reconstructions today, all the extraction itself and all the squares optimization that typically happens in the background, that's pretty quick to do. The key limiting factor is actually the search for correspondences, because there are so many possible combinations how you can combine Sift feature number 1 in image number 1 with Sift feature 15 in image number 200. And the combinations that you have, this grows so quickly that it's really hard to track them down. But here, the beauty of Sift actually kicks in by having those signatures. And the trick is to not basically look through all your features, but basically try to search in the space of signatures. And there are some ways how you can do this in an efficient way, some efficient data structures, how you can look for similarly looking signatures quite quickly. And this dramatically speeds up the computation, but still is the most time consuming task.
Right. So are in your work, like, I mean, you're doing robotics and things like this. Is Sift now pretty much like a standard package that somebody pulls off the shelf and then they put it in, or are there still people that are working on improving it or doing different things with the Sift algorithm?
So absolutely. So there's a big development ongoing actually right now. So Sift itself is still kind of an absolute standard. So if you propose a new feature descriptor, you will always have to compare against Sift. That's clearly the point. And we see 2 developments here. One development is towards those binary descriptors. These are descriptors which are much more compact, much faster to compute, and really target mobile applications, lightweight compute, where you want to track features, for example, moving a camera through the environment, and where you not necessarily want to recognize something again after extended periods of time or something like this. So they're really made for high-speed computation. That's kind of one direction. Whatever BRISC or B, all those types of features are these kind of binary features.
Okay.
And then there's another development which stems from or benefits from the deep learning developments that we see since the last 10 years, so that we have a lot of algorithms which try to solve things like place recognition or extracting semantic information from images. And those deep neural networks, they actually learn a feature representation in the process of performing the actual task. And those descriptors are typically then global image descriptors, at least most of them. That means they encode the whole image, but they also turn out to be fairly advanced and fairly robust for doing certain tasks. So there are now features which are learned, which beat Sift on a lot of disciplines, just as a result of this kind of deep learning byproduct that the classifiers also learn a feature representation for solving the task. I mean, Sift is still an absolute standard today because it doesn't need to have any training. It runs out of the box. It's fairly fast. It's actually performs really, really well. Also, the patent it was patented for a while, which caused some issues. I think the patent has expired last year now, so you're more free to use it. But if you look for really high quality stuff, then there are other learned representations that can be better.
I see.
But it depends a little bit of your task at hand.
Okay, I was going to ask you about your work. Like, what kind of research or what kind of things are you currently working on? Just aside from Sift?
Yeah, so I have a group here of we are approximately 20 people working again in the intersection between robotics and photogrammetry. So we basically have 3 application domains in my lab. So one looks into autonomous driving, and here especially the perception part for that. So we look into how to interpret the scene, what do we see, what are objects around. For that we use also a lot of learning techniques. So this is a key role. A second part is agricultural robotics. This is where we are also in Bonn heading a very large, we call a cluster of excellence, basically very similar to these AI institutes, national AI institutes in the US. So a large scale funding body for agricultural robotics or robotics and phenotyping towards more sustainable agriculture and crop production. So a lot of the activities is UAV-based inspection of fields, deriving phenotypic traits, identifying what's going on in the field, doing automatic assessment, so that we can, for example, then trigger automatic management actions or support breeding. And the third area is traditional service robotics. So this can be robots operating in hospitals for providing services to doctors or to patients, logistic tasks, transporting dangerous probes, which is probably, we gained some popularity with that in the last 1.5 years. So these are kind of these 3 areas that we are working in. And technique-wise, a lot of is sensor data interpretation, mainly working with cameras or working with LiDAR data or combinations, so depth cameras as is one example. And then using often either learning algorithms or probabilistic algorithms, so algorithms relying on probability theory in order to perform state estimation tasks and selecting as optimal actions as we can select.
Yeah, so that's interesting. So, you talked about like machine learning and things like this. And how do you see some of that possibly making its way into, let's say, just standard photogrammetry? Like what can it do for photogrammetry, for example?
Okay, so it can actually do a lot. So if you look into the field of photogrammetry, you basically say it's measuring with images. So that's where what the name, or measuring with light, what the name actually says. And we are doing a lot measuring with images, but also kind of other sensors such as LiDARs or laser range scanning plays an important role. There are certain things that we know how to do really well. So if you think about solving least squares problem, which is a technique which sits behind bundle adjustment, so basically computing 3D configurations of cameras and points in the environment, we can actually do that really well with standard techniques. But there are other things which we can't formalize that well, where learning is really the solution from my point of view. And this is for all the tasks that we cannot specify that perfectly. So one of the things could be semantic interpretation. So besides geometry of basically what's the 3D shape of that object, basically what is it what we are seeing here? Is this a person? Is this a dog? Is this a chair? Is this a door? This is super hard to formulate as an equation. And here learning approaches play an important role. Yeah. But also in the geometric reconstruction, we see more and more developments automating some parts of the process using learning algorithms. For example, this search for correspondences or finding what actually is the same in an image. We can define it based on intensity values, how similar are the intensity values, but that's actually quite tricky to do. If you can learn that, that has clear advantages that certain processes can be learned because they're hard to formulate, and certain tasks we know really well how to solve them, and their learning plays a smaller role, although still people try to tackle that with learning as well.
Yeah, that's really interesting because so just yesterday I received some images from somebody who wants me to create a model from something, and it's just something that somebody happened to snap, and it's a forensics case, right?
Yeah.
So, but in looking at the images, it's very clear to me where the correspondences are, right? So I can see an image was here, but you put it into photogrammetry software. I don't have a lot of photos, and it fails every time. And so I was thinking, geez, like I can tell that this is the same object from a different location, but you know, so I was thinking, geez, you know, this is really where machine learning could really help, or you know, some more intelligent system that could do something like that. So for example, even so, like you were saying with Sift, maybe it could be, you know, Sift on steroids by implementing some of that stuff. But are there people working on that now?
Yes, absolutely. So they're basically all the people who use their neural networks in order to do some task with it, could be semantic interpretation or anything, they need to learn a feature representation. And it turns out that the feature representation that you generate, for example, for place recognition task is also super useful for identifying other things. And so on the one hand side, it's a byproduct that is generated from those learning algorithms, but there are also people who explicitly try to optimize features, reproduce results similar to Sift, and then optimize them further to be more distinctive in certain applications. So a lot of activity is ongoing, because if you have really good features, that makes your life easier later on down the line. You realize this already. If you have better correspondences for your applications, it will improve all the reconstruction, all the interpretation for that forensics case, for example, because you just have better correspondences in the first place. So there's a big gain for optimizing for that.
Yeah, I was trying to think about the kinds of things that can get you in trouble when taking these types of photos. But I was wondering if there was something unique to Sift, which may cause it to break down, or may cause it to fail in some cases. But it's actually, I'm surprised at times at how robust it actually is in finding features, and then even finding correspondences. But is there anything that you can say about Sift, like sort of certain thresholds or certain limits where it's like, yeah, it doesn't work, after this point, kind of thing,
So let's say this: we have to look where what Sift is actually doing. So Sift looks into distributions of gradients in the local surrounding. So you have a distinct point, let's say a corner somewhere. So it takes whatever 32 by 32 pixels around that corner and says, okay, where are those gradients? How do the gradients look like in this local region? So if you have repetitive patterns in your scene, you're quite likely to actually screw up Sift. So let's say you have a beautiful facade, which has a lot of repetitive structure, like in Venice and one of those big palaces, and everything is repetitive. That's actually really, really difficult for Sift to do. And so because it will just generate local descriptors which look very similar to the other part of the scene. However, you can also use tricks for that by saying, okay, let's do the association only with features where there's no ambiguity. You basically look at what's the best matching Sift feature and what's the second best matching one. And if they are still similar, then I say, okay, I better not touch that type of descriptor and ignore them for now, because I can't disambiguate them. And as long as you see enough of non-repetitive structures to make a first alignment, you're safe. But if everything is very repetitive, then your system is very likely to break.
Well, that's something that you see in practice all the time. So, yeah.
I mean, let's say if you have, for example, a setup where you have an initial guess for your camera. So if you don't take pictures completely independent from each other, but you're actually moving a video camera, so to say. That's something that happens often in robotics. The robot doesn't take just pictures once every 5 seconds from a viewpoint it thinks it's good. Just let the camera run and track how the camera is moving. And this allows you already to get a pretty good initial guess how the camera is oriented, which then helps to actually eliminate potential ambiguities in your feature descriptors.
Right. So if taking photographs, then it helps to have small incremental changes between the different photos. So it kind of leads it in. You don't have this great disparity between, all of a sudden you're at an image, and then all of a sudden you're at 90 degrees to the object. And okay, you have a big book. Yeah, that seems pretty clear. So in terms of future research and the kinds of things that you're planning to do yourself, I mean, you obviously teach. You're doing a bunch of video. You're busy online with becoming a show, almost a celebrity online. And
Yeah.
and what about future research? What do you have planned?
Okay, yeah, no, we are actually working really actively in this interpretation and prediction how the future will look like. So whenever you observe your local surrounding, you can actually estimate what's happening there. You say, okay, that's a person over there. This is whatever, a car driving. But the question is, how does the world look like in 5 seconds? Which is not too difficult for us as humans to anticipate what's going to happen, but that's still a quite challenging problem for computers. And you need that especially, for example, for autonomous driving. You want to know how the scene looks like, or what it looks like in 5 seconds in order to make appropriate maneuvers. That's kind of a very interesting
So you mean
question.
considering like people are moving, cars are moving,
Exactly.
so you have to predict where everything's going to be.
Yeah, exactly.
Gotcha.
So this is one challenging thing. And the other thing, what we are also dealing with, especially in the agricultural domain, is the world is changing very slowly here, like plants grow, but they change their appearing quite substantially. If you're on a field today, next week, in 2 weeks, and you actually want to identify every individual plant, see how it's doing, is it healthy, does it need special care, is weeding needed, or fertilization, or some pest control, and making this analysis is still a quite challenging task. And if we can automate that, we can, of course, automate a lot of activities that we are doing in agriculture, where we right now use just massive amounts of agrochemicals. For example, for weeding, we just spray our field with a herbicide to get rid of the weeds. If we can identify that instantly in a fraction of a second with our camera, which we can do right now, we can do other cool stuff, whatever, using a laser and burning away the wheat, or using a mechanical stamping tool for stamping it away. That's still already doable for the weeding context, but gets much more challenging if you think about nutrition deficiencies for fertilization, or certain pests, which if you see them, it's already too late. So one of these early detection tasks, they are also very challenging and can really make a big impact on what we can do with robots. So there are really a huge number of challenges which are out there in this intersection of robotics, image interpretation, computer vision, machine learning, AI. I mean, a lot of things are ongoing there.
I'm just trying to imagine on an agricultural field. So I mean, these are huge, massive landscapes or whatever. So what camera are you using? Like, it's an up close camera that kind of robotically goes up and down, or does you fly something, or what do you?
So we have different applications. So most of the stuff that we are doing right now is actually a drone, and we use really high resolution cameras, 100 megapixel cameras, for example, so that we can fly as high as possible, but still have a very high resolution, so that we can do a lot of the image interpretation tasks. So we are flying with a ground resolution of, let's say, one millimeter per pixel approximately. And this allows us to actually do all the weed analysis easily. We can even start to detect some of the diseases out there with those cameras. You can use multispectral, hyperspectral sensors as well. They are the resolution is lower, they're a bit harder to handle well, but they allow you to see kind of outside the visual spectrum, which is especially relevant for plants. But if you actually want to execute some activities, some management actions on the field, you will probably do that on a ground vehicle. So we are doing a lot of monitoring, and then with a drone, and then redirecting the robots on the ground for doing targeted intervention at certain locations in the field, for example.
All right, really interesting. Great. Well, I'll tell you what, we're getting on almost to the half-hour mark here, and I didn't want to let this go on too long. I think we both have commitments too, but if somebody wants to get a hold of you, they can just go to your website, actually. Let me bring that up here. This is up here. Actually, you know what I'm going to do? I'm actually going to copy that and make that available so people can see it nice and big. And let me see if I can do it. Oops, that's not what I wanted. You're also on LinkedIn, yeah?
Yes, exactly. LinkedIn and YouTube are two channels. So on YouTube are most of the videos, or all the videos, obviously, like this 5-minute series, but also most of the lectures that I'm teaching are actually available online.
Oh, they are too. Okay, great. I'll have to look at some of that too. I've been following a few of the 5-minute stuff. 5 minutes is very convenient, but in some cases I'm like, damn, I wish he did more on that one. So I may have to look. Yeah.
It actually started for giving students material to prepare before coming to the lecture. So we always wanted to do that, but it was very hard for students to follow up on that. And that kind of the idea on this 5-minute series was actually to have something that you can actually watch on the way to the lecture in the bus or in public transport, and at least be a bit prepared for the lecture. And it just got very popular, but it really started as additional material for teaching originally.
That's a great idea. I like that. So, well, listen, thank you very much for being here. Hang back here. I'm just going to do the closing remarks, but hey, really appreciate your time.
Perfect. My pleasure. It was great to be here. Thank you very
All
much for
right.
the invitation.
Cheers. All right, folks. Well, that does it for this episode of Click 3D. Don't worry, there's going to be another one coming very, very soon. So thank you for watching, and we'll see you next time. Bye-bye.